Good morning, everyone. Hope all is well. Hope everyone's doing all right. All right. Looks like everybody is connected. Hope everybody had a great weekend, ready to get this week started. Any questions, general questions, any math questions, anything before we get rolling? Hold up, see somebody in the chat. Okay, yeah. I know I'm going out of town this week. We should be back by Friday. Shoot me that email if you don't hear from me before, by like we normally do Thursday afternoon. If you don't hear anything from me, shoot me an email to confirm that. I should be able to do it. I think I'll be back in town by Friday. So for those who are not seeing in the chat, one of your classmates asked, will there be an opportunity to take a test this Friday? So like I said, I'm going out of town this week. As a matter of fact, Thursday, we will not be able to have, well, not Thursday, Wednesday. I'm gonna send an email, but I believe Wednesday we won't have class because I have to go out of town. So, but I believe I'll be back by Friday. So I'll shoot you an email on that, reminding you guys about Wednesday, most definitely. But for Friday, if you don't hear anything about that by Thursday afternoon, make sure you shoot me an email to remind me about Friday to confirm that we will be able to do a test for those who are looking for the opportunity to take a test on Friday. All right. Anything else? Anybody else? Anybody have a problem? Anything?
Mr. Tucker, Friday at the same time, 10 to 12?
Yes, that's what it'd be.
Okay, thank you.
Not a problem. Everybody good? Everybody straight? Okay, let's see. Where did we leave off in our notes? All right, so complex without 7, 6. So we only have one section left out of this chapter. All right, hold on one second. Let me confirm before I do 14.7. Let me check one thing. Okay, so that's what I was missing. So 14.6, you guys aren't held accountable for. I knew we did 14.5, but I forgot that 14.6, you guys aren't held accountable for. So, because I thought it was, I knew we did 5. I just knew we had to go to 4.7. So Okay, so we only have one more section left out of chapter 14. And then that'll be it for chapter 14. And guess we'll look at one section out of 17 today as well. Unless, some people had questions or whatever, but yeah. So let's go ahead and look at 14 some. So complex fractions. And the reason why they call it complex fractions is because you have a fraction on top, a fraction on bottom, and then this whole thing is a fraction itself. So, when one fraction is just 4 over 5, that's just a simple fraction. But once you add another division bar, then it's considered complex. All right, so looking at the first way of dealing with our complex fractions, call it method 1. Notice how we have one solid fraction over one solid fraction. Whenever you have that scenario, you can just go ahead and set it up this way. In other words, this one is written vertically. This is the same problem written horizontally. And that division bar is the same thing as this division symbol right here. All right, so you see we haven't changed the problem at all. All we did was go from writing it vertically to writing it horizontally. All right. So now when it's in this form, we talked about it before, whenever dividing fractions, you're going to multiply by the reciprocal. And I didn't say what I had here. Sorry about that. This is 4w squared over 5sr, or 5rs, excuse me. And this is 20 WR over S squared. So this is the only 5. And these other 2 are S's. So once again, this is the 5. These are S's. All right. So like I said, you're going to divide, whenever dividing by fractions, you multiply by the reciprocal. So notice that the division sign changes to multiplication. And then the 20 WR over S squared flips. And now it's S squared over 20 WR. All right, any problems? All right, so now we can look to simplify. Let me erase this stuff so we can see what we have. So I just broke down each piece. W squared is just W times W. I left the 4 as is because I know there's a 4 in the 20. And so that's what I did here. See, the 4 is broken down to 4 times 5. So cancel out the 4s that are in common. I have 1 S. That's in common with the top and bottom. I have 1 W. That's in common with the top and bottom. And then looking at what we have left, we have W and S in the top. Down bottom, 5 times R times 5 times R. And that gives us this result, WS over 25 R squared. All right, questions on that before we do another one? All right. So same thing here. We have y minus 8 over 5y over 3y minus 24 over 15. So once again, we have one solid fraction over one solid fraction. So we can use method 1, which means that I can rewrite this horizontally And this is the same division sign. Change division to multiplication, flip this fraction. Then we factor. So in the first fraction, there's nothing for me to change or factor. I broke up the 15 into 3 times 5. And I'm mistaken, deleted 8. Then that 3y minus 24 is 3 times y minus 8. I can cancel out what they have in common. Y minus 8 cancel. 5 cancels. And then also this 3 cancels. So when everything cancels, don't forget that you're left with 1. And then down bottom, you have y. So the result is 1 over y. Any questions? Any questions? All right. Any problems before we look at the second method? All right. So the second method is what you would have to do. I don't have to do because you don't necessarily have to do it. Because if you really wanted to do the first method, what you could do here is combine this to 1 fraction, combine this into 1 fraction, and then do what we did here. But I like method 2 because we don't have to do that. What we would do is first find the LCD. And in this case, the LCD is A. We have B over A plus 7B over B plus 2B over A. So the LCD is A. And then we've done this process before. We're going to multiply each numerator by the LCD. So each numerator, we're going to multiply by the LCD. All right. Then put, didn't put that, okay. All right, so multiply each numerator by the LCD, and then we'll simplify. So the A's will cancel in that first term because we had AB over A. This one stays the same. There's nothing you can do with that. Then down here, this stays the same. But over here, we have A's cancel. And this is our result from the simplification. All right, B plus 7AB over AB plus 2B. And then, we still want to factor if possible. And that's what we're doing here. So we factored out a B from each. So took a B out of the numerator, left us with 1 plus 7A. Took a B out of the denominator, left us with A plus 2. B's cancel, And this is our final answer. 7a plus 1 over a plus 2. All right. Question with the process. Everybody doing that one? All right, so this next one is 8 over x squared plus 1 over x over 2 over x squared minus 1 over x. All right, LCD this time is x squared. We have x squared and x as our LCD. So you take the highest, I mean, not as an LCD, as our denominators. So then you just take the highest representation of x, which is just x squared, and you multiply that to each numerator. And that gives us what we have over here to the right. So we have 8x squared over x squared plus x squared over x, 2x squared over x squared plus x squared over x. All right, so we're going to cancel out what we have in common with each. So I'll just write this. All right, so our x squareds cancel out, leaving us with just x. One of the x's cancel here, leaving us with, I said leaving us with just x. Let me go back. X squareds cancel out, leaving us with just 8. One of our x's cancel out here, leave us with just x. That's what I was thinking about. I said it too early. Then here, x squareds cancel, leaving us with just 2. One of the x's cancel here, leaving us with just x. And that's the result. All right. Questions before we do another one? All right, so here we have n to the negative second power minus m to the negative second power over m to the negative first power plus n to the negative first power. So we want to rewrite these terms without negative exponents. We want to write them as positive exponents. So the way we do that is dropping that n to the negative second power down to your denominator. And so this is the rewriting of each one of those as a positive exponent. So you drop it down to your denominator to turn the exponent positive. And just like before, when we had x and x squared, your LCD is going to be a combination of the highest power of the variable that you see. So you notice we have n squared and n, so we use the n squared, the m squared and m, so we use m squared. So that's why our LCD is m squared, n squared. All right, any problem with that? So then we go ahead and multiply m squared, n squared to each numerator. And this is the result. with our cancellation. Notice the n squared cancels out completely in the first term. Then m squared cancels out completely in the second term. One of the m's cancel here. One of the n's cancel here. And that leaves us with this result. All right, m squared minus n squared over m n squared plus m squared n. And in our numerator, we have difference of squares. Denominator, we can factor out the GCF of mn. And so this was the result with m plus n being able to cancel out. And this is our most simplified way of expressing our expression. All right, any questions? All right, everybody okay? All right, next one, 1 minus 1 over x minus 6 over x squared, 1 minus 10 over x plus 21 over x squared. Looking at an LCD of x squared, once again, the highest power of x, or highest power of our variable is going to be our exponent. So we'll multiply each numerator by x squared. So multiply each term by x squared. It gives us x squared minus x squared over x minus 6x squared over x squared over x squared minus 10x squared over x plus 21x squared over x squared. So in the middle of each, only one of the x's will cancel. And then on the right of each, far right, x squared cancels out completely, leaving us with this expression, x squared minus x minus 6 over x squared minus 10x plus 21. Then we factor each. X minus 3, x plus 2 is our numerator. X minus 7, x minus 3 is the denominator. X minus 3 is cancel. X plus 2 of x minus 7. All right, any problem? I think we got one more. Everybody done with this so far? Scroll up. Okay, that's from another section. Oh, that's another section. Okay, it's rehashing the other way. Okay, yeah, so this one is the last one. Okay. All right, so here we have 11 over x plus 10 over x plus 1 over 10 over x minus 11 over x plus 1. So our LCD is going to be a combination of the two different denominators that we see. We have x and x plus 1. So I'm going to multiply once again each numerator by x times x plus 1. Whatever your LCD is, you multiply each numerator by that. So multiplying each numerator by x times x plus 1 allows this x to cancel, x plus 1 to cancel, x to cancel, and then x plus 1 to cancel. All right. So that leaves us with x times x plus 1 plus 10x over 10x plus 1, 10 times x plus 1, excuse me, minus 11x. Now we can distribute and combine like terms. Distributing gives me 11x plus 11 plus 10x. And then here 10x plus 10 minus 11x. Combine your like terms, 21x plus 11, 10 minus x. And that is it. Nothing else we can do with that. Any questions? Any questions? Any questions? Any questions? All right. So our next section we're going to discuss, we'll at least look at 17.1, radical expressions. Okay. Let me see here. Before we go, let me see 18.2. Yep. Okay. All right. So let's look at radical expressions. So what they want to emphasize initially is that the square root, whatever root you have, can be rewritten as a fraction in your exponent. So square root can be rewritten as x to the 1/2 power or the 1/2 power. And these square roots, third cube root, fourth root, they're called radicals. So that's why we're talking about radicals. And so the cube root would be x to the 1/3 power, fourth root 1/4 power, and so on. So even if you had the 100th root of x, that would be x to the 1/100 power. All right. Is everybody okay? So just to reemphasize the radical process, if you have the square root of 64, 64 is called the radicand, just in case you were to see that term. What's under the radical is always called the radicand. So he's saying what times itself twice, because our index is 2 right here. When you don't see anything, assume you know there's a 2 there. All the rest of them will be shown. So cube root, fourth root, fifth root, sixth root, you will see a number. But when you don't see anything, they assume you know there's a 2 there. So what times itself twice will give you 64. And the answer to that is 8. So that's why the square root of 64 is 8. But if I had the cube root of 64, what times itself 3 times? Because I have a 3 right here. What times itself 3 times will give me 64? And the answer is 4. Because 4 times 4 times 4 is 64. All right, question on how these radicals work. All right. All right, so here just re-emphasizing the process and also what occurs if you have a negative under the radical. Square root of 121 is going to be 11 because 11 times 11 gives you 121. But if I had the square root of negative 121, your answer in this section will be not a real number. I think this class goes into imaginary, but if not, we know right now the answer is not a real number because there's no such thing as a number times itself twice that will give you a negative number. Because here, negative 11 times negative 11 will actually give you positive 121. So there's not a number times itself twice that will give you a negative number. So that's why we were right, not a real number. So whenever you're taking the even root, and we'll get more detail about it right now, we're just talking about square root. But if you're ever taking the even root of a negative number, it's not a real number. But here, notice the positioning of our negative. If the negative is on the outside of your square root, then you can take the square root of the 121 because it's not affected by the radical. So that's going to be negative 11. Once again, notice the negative is sitting on the outside, never affected by the square root. So make sure we're okay with the positioning of that negative. If it's under the radical, not a real number. But if it's on the outside, it doesn't affect anything. All right, so here, so this is between dealing with an even root versus an odd root. Here we have the cube root of 8. Cube root of 8 is 2 because 2 times 2 times 2 will give you 8. But the cube root of negative 8 will be negative 2 because negative 2 times negative 2 times negative 2 will give you negative 8. So you can take the odd root. Notice our root is odd. The index of a radical is odd. You can take the odd root of a negative, cannot take the even root of a negative. And here's just re-emphasizing that Here we have the even root. Once again, we have the fourth root of 81. Fourth root of 81 is 3. Because 3 times itself 4 times will give you 81. But then the fourth root of negative 81 is going to be not a real number. Going back to that even versus odd thing that I was mentioning before. Because negative 3 times itself 4 times will give you a positive 81. Once again, fifth root, which is odd. Fifth root of 32 is going to be 2. Fifth root of negative 32 will be negative 2. And I'm summing the even odd thing down here. I'll give you a chance to write that down. All right. Anybody still copying? All right. So the even index or radical cannot take the root of a negative number without the result being imaginary. Odd index of the radical could take the root of a negative number. So just trying to sum up what we were saying there. So you can take the odd root of a negative number, cannot take the even root of a negative number. And problems. All right, so in this section, they also talk about using absolute value. Whenever you take the nth root of x to the nth power and n is even, then they want you to use absolute value of that variable or that result. But if n is odd, then you just use what you have or whatever the result is. So I'll show you what that means in a second. But the key, once again, is if it's even, we're going to look to use absolute value. If it's odd, then we're just okay dealing with the result that we have. And so what it comes from is that you look here at this example, 5 times 5 is 25, negative 5 times negative 5 is also 25. So what it's saying is that they want the result to be positive, because actuality, if I took the square root of 25, I could write negative 5 as my answer, because negative 5 times negative 5 is also 25. But they want the positive result. So that's why we're using the absolute value when it comes to our even powers. So when we look at the square root of x squared, square root and square will cancel completely, but the result is that they want to be the absolute value. They want you to have the absolute value because it's even. Remember we say if we do even, going back here, if it's even, nth root of x to the nth power will cancel out completely, leave you with just x. So what you want to have is x to the with absolute value of x. So that's what we did here. Also, this is what we're doing right here. The fourth root of x to the fourth root and the fourth power cancel out completely, leaving us with just x. But because it's even, we're doing the absolute value of x. So now if it's odd, which is what we did right here, the cube root of x cubed is just going to be x. Because it's odd, all you have to do is write down x right here. The 101st root of x to the 101 power is odd. So all you have to do is write x here. Because it's even, we have to do the absolute value. The result has to be the absolute value of x. So once again, odd, you can just write down the simplified result. If it's even, you have to do the absolute value of that result. All right. Same thing. Oh no, what did I write? What did I just do? Okay. All right. So same thing happens here. We have the square root of a plus b squared. The square root and the square will cancel out completely, leaving us with just a plus b. But because we have this index of 2 here, assuming you know it's the 2 right here, absolute value of a plus b. And I wrote right here because of the even index. Here, 13th root of a plus b to the 13th power. Odd, so the result is just a plus b. All right, any questions on that? All right. All right, so here, simplify, and then it says assume all variables are positive real numbers. So now when it says that, and that's why I underlined it, when it says that, assume all variables are positive real numbers, that means that this up here and all that we don't have to hold on to because we're assuming they're positive. Remember, the only thing the absolute value does for us is ensure that we have a positive result. The absolute value of 5 is 5. Absolute value of -5 is 5. But if we're going to assume all values are positive, so you see those directions, you don't have to use the absolute value. And that's what I'm pointing out right here. The square root of x squared is just going to be x if we're going to assume all variables are positive real numbers. And so after this exercise up here, really that's what they're going to have in the directions for the most part. You're going to assume all the variables are positive real numbers. All right. Any questions on that before we look at a real problem? All right, let me erase this, put it back. All right, so we have the square root of 81, a to the 8th, b to the 6th, 9, and c to the square power. C squared. Yeah, it's a c to the square. C squared. All right, so we're going to take the square root of each one of them individually. So that's what I did right here. Whether you write it out or not, you know, this is the process, the thought process that you should take on. And so the square root of 81 is 9. But when it comes to our variables, we're recognizing that we have a 2 as the exponent, or 2 as our index. That means we're going to take each one of those to the 1/2 power. So I'm going to be dividing each one by 2, each exponent by 2, and that leaves us with this result right here. Since we had a to the 8th, divided by 2 is a to the 4th, b to the 6th, we'll turn to b cubed, and then c squared. 2 divided by 2 is 1, so it'll just be c. So whatever that index is, you will be dividing by the index for your variables, for the exponents of your variables. All right, so here we have the 5th root of 32, x to the 20th, y to the 15th. So the 5th root of 32, what times itself 5 times will give you 32 is 2. Then we'll divide these exponents by 5, because it's the index of our radical. 20 divided by 5 is 4, 15 divided by 5 is 3. And this is the result, 2x to the 4th y cubed. All right, any problems? All right, same type of deal here, just that we have a fraction involved. We have the cube root of 27, x to the 21st, over 125, y to the 39th. So we take the cube root of each piece individually. And that's what we did right here. So the cube root of 27 is 3, because 3 times itself 3 times will give you 27. X to the 21st, we're e to the 1/3 power. We're just dividing that 3 into 27, leaving you x to the 7th. Cube root of 125 is 5. 5 times 5 times 5 is 125. Then the cube root of y to the 39th power is y to the 13th. All right, any questions? All right, everybody's good. Let me see what 17.2 is. Same type of stuff. Huh? Okay, 17.2 is not that long. We can knock that one out as well. All right, so let's look at 17.2. Still piggybacking off of what we did in 17.1, rational exponents. And then we'll look to call it a day. So the square root of x, x to the 1/2, we already talked about that relationship, but that holds true no matter what you have as far as your the application of that square root. So here we have 36 to the 1/2 power. That's the square root of 36, which is just 6. Okay, so you can go, use it either way, whether it be as an exponent or as a radical. All right. So same thing here. If I have 343 raised to the 1/3 power, cube root of 343 is 7, because 7 times 7 times 7 will give me 343. Any problems? All right. 625 raised to the 1/4 power. Fourth root of 625 is the application. And that'll be 5 because 5 times itself 4 times will give you 625. Okay, so here we have a negative exponent. To turn it positive, you drop it down into your denominator. And then taking the square root of 36, that'll be just 6. So we have 1/6. All right, here 1000 raised to the negative 1/3 power. So same process. Drop that 1/3, that 1000 to the 1/3 power down into your denominator to turn that exponent positive. And that's going to be 1/10. Now in this, why is my pen working funny? Okay, there we go. So now this one right here, we have negative 1/3 raised to the negative 1/3 power. Just want to make sure I emphasize that these two negatives have nothing to do with each other. So a negative to a negative in this case doesn't turn positive. They're not being multiplied. You know, one is an exponent and one is sitting in front of your whole number. I won't say whole number. Your integer. Yeah, your integer. So all you do is drop it down to your denominator. That's what this negative tells you to do. But this negative is still here. And so then that will be 1/-10, which is the same thing as negative 1/10. All right, any problems with that? All right. Okay, next thing in this section that they introduce is actually having a fraction as your exponent that has a number other than 1 in the numerator denominator. So if that's the case, always you can apply them in any way. If you're using the calculator, it doesn't matter. But if you're doing it by hand, it may matter. You know, one way may be easier than the other. But as long as the numerator is your power and the denominator is your root, you still get the same result. So if you take the x to the a to the power of a first, or the 8th power, and then take the bth root, it'll be the same thing as taking the bth root first and then raising it to the 8th power. As long as the a is the power and b, your denominator, is the root, you still get the same result. So that's what I did right here with the 8 to the 2/3 power. You have the cube root because the 3 is your denominator, and then 2 is your power. So notice in the first one, I took the cube root of 8 first, which is 2, and then squared it, and it gave me 4. And then here in the second one, I took this, I squared 8 first, which is 64, and then took this cube root of 64, which is still 4. So either way, we'll get 4. But the order in which you apply your exponent doesn't matter as long as your denominator is your root, numerator is your power. Any questions? All right, so the next one, let's say we have 49 raised to the 3/2, or 3/2 power. If I was doing this by hand, I would take the square root of 49 first and then cube that. And that's what I did right here. Square root of 49 is 7, then 7 cubed, 7 times 7 times 7 is 343. Now, if I was doing this by hand, what I would not do is cube 49 because you're talking about dealing with familiar numbers. I'm not familiar with 49 times itself 3 times. And then after that, I would have to take the square root of that. So that's the difference between doing it by hand versus doing it in the calculator. Like I said, if you do it in the calculator, all you're doing is throwing this in the calculator, you get your result. We're talking about which one would you choose, which order would you choose. It only matters if you're actually trying to calculate this thing by hand. So once again, if I was doing it by hand, I would take the square root of 49 first, then cube the 7, and that will give me 343. Once again, if you're not doing it by hand, it really doesn't matter which order you do it in, as long as you remember that the denominator is your root, numerator is your power. All right, here we have -4 raised to the 3 power. Doesn't matter which order you apply this. If you hold true to the idea that your denominator is your square root, because you have a 2 in the bottom, numerator is your 3rd power because you have 3 in the numerator, you're going to end up taking the square of a negative number, no matter what order you do it in. And the result is not going to be a real number. So you don't have to go all the way to the end here. Once you recognize you're taking the square root of a negative number, your result is not a real number. All right. Questions on that? All right, the next one, we have 1/16 raised to the 1/4 power minus 1/81 raised to the 1/2 power. Excuse me. Sorry, I had a sneeze. Sorry about that. So if we take the 4th root of 16, that gives you 2. Of course, the 4th root of 1 is just 1. And then the same thing with the 4th root of, not the 4th root, but the square root of 1/81 would be 1/9. All right. So then what we have is 1/2 minus 1/9. Don't forget, if we're going to add or subtract fractions, we need a common denominator, which is 18, because 2 times 9 gives us 18. And then from there, we're just doing our regular arithmetic of subtracting fractions, multiplying top and bottom by 9 in the first one, top and bottom by 2 in the second one, to give me 9/18 minus 2/18, which is 7/18. All right, any questions? Can we scroll up? Anybody still copying? All right, so in the next one, we're going to be simplifying with these fractional exponents or rational exponents. So don't forget your exponent rules. If I'm multiplying like variables with the same variables, I'm going to be adding my exponents. So if I have x to the 1/3 times x to the 5/3, that means I'm going to add my exponents of 1/3 plus 5/3. That'll give me 6/3. And then 6 divided by 3 is 2. So my result will be x squared. All right. So once again, applying your exponent rules, I have 7 to the 1/3 divided by 7 to the 4/3. Whenever dividing, we're going to subtract our exponents. Remember, it always matters if we have like bases. It only applies to like bases. So 1/3 minus 4/3 give me -3/3. -3/3 is -1. To make that a positive exponent, drop the 7 down to your denominator is 1/7. All right, any problems? All right, next one, x to the 2/3 times the quantity of x to the 1/3 minus x to the 5th. Going to distribute x to the 2/3. That will give us this result. X to the 2/3 times x to the 1/3 minus x to the 2/3 times x to the 5th. And once again, whenever we multiply like bases or like the same variable, we're going to add our exponents. So 2/3 times 2/3 plus 1/3 here, and then 2/3 plus 5/1 here. 2/3 plus 1/3 is 3/3. But over here, I did the work for 2/3 plus 5/1. Don't forget you need like denominators. So we had to turn that 5/1 into a fraction with the denominator 3. So that's going to turn to 15/3. Then 2/3 plus 15/3 will give you 17/3. So that's how we got here. And then 3/3 is 1. So it's just x to the first power. And then that's minus x to the 17/3. All right. Questions on that result? All right. Any questions? Any questions? Okay, so that's it for 17, what 17-2, I think. Try this stuff out as always. See if you get stuck. If you have any questions, feel free to ask. And yeah, well, that'd be good for us. That's 3 sections. I don't want to overdo it. Did anybody have any questions before we close out today? Everybody good? Everybody straight? So next class, we'll get into, like I said, I believe this is 17 for us. Yeah. So next class, we'll get into 17.3, simplifying radical expressions. More stuff along the same lines of what we just finished doing. Just adding a little bit more to it. And then we'll go from there. Didn't mean to do that. There we go. So you guys have a good one. Be safe. I'll shoot you that information on Friday. Like I said, I should be back in town by Friday. If I have any snares or hiccups, then most definitely I'll let you know for anybody who's going to try to take a test. And outside of that, don't forget you can get with Mr. Davis with taking the test. If you have, well, I don't know if anybody been trying since I've been, giving you guys opportunities. But if you have any issues with getting with him, feel free to let me know. Then we'll make sure that's straight. Other than that, you guys have a great day. Be safe, and I'll talk to you soon.
Y'all have a nice one.
Thanks. You do the same.
Thank you.
Take care.